So what were the findings of Oersted's experiment then? The findings were that electricity, in this case, electricity basically produced magnetism. That means we got magnetism out of electricity. That was the finding of Oersted's experiment. In electromagnetic induction, however, we ask the reverse question. The reverse question as in this case, we got magnetism out of electricity. In case of electromagnetic induction, we ask whether we can get electricity out of magnetism or not. If you ask this question, the answer lies in this topic, which is electromagnetic induction, which we will learn now. So moving on, if you ask the reverse question, there is another experiment which will give you the answer. The experiment is named after a famous scientist, Michael Faraday. We call it Faraday's experiments. What were these experiments? We will try to figure out. Now, in Faraday's experiment, there is this loop. It is connected to a galvanometer, and there is a magnet near it. So it is North Pole and it is South Pole. Now observe here, there is not a single battery or cell connected in this circuit, only a circular coil connected to a galvanometer. What does a galvanometer do? It basically detects and give you the direction of current in a circuit. So in this case also, since there is no battery, if somehow we are able to implant or induce current in this circuit, this galvanometer would show deflection. But since there is no battery connected to it, there is no point of having electric current. But you will observe that when you move this magnet towards the coil or away from the coil, when you move this magnet towards the coil and away from the coil, then this galvanometer shows deflection. Of course, if you move the magnet towards the coil, it shows a deflection in one side. You take it away from the coil, it shows the deflection in the opposite side. So that's pretty strange. Without any battery, you are able to induce current just by moving a magnet. What happens if you keep the magnet fixed? Well, in that case, there will be no deflection by the galvanometer. That means there will be no induced current. So the current is induced only when we move the magnet towards or away from the coil. So next up, we again take another coil. Now with this coil, there is a battery connected to it, like this. There is a battery connected to it, so of course current will be flowing through this coil. Let's call it C1 and let's call it C2. So leave the magnet. Even in this case, if you move C2 towards or away from C1, then also the galvanometer shows deflection. If you keep the coil fixed at this position, there is no deflection by the galvanometer. So here the movement of the magnet or the movement of this coil is important for having induced current. Why? The answer lies in the definition of electromagnetic induction. What is the definition of electromagnetic induction? It basically says that whenever you change the magnetic flux associated with any coil, then electric current is induced in that coil. So the key point here is change in magnetic flux. See, it is pretty evident from our experiments. So when you change the magnet, when you take it towards or away from the coil, what you are doing? You are changing the magnetic flux associated with C1. as a result you are having electric current in the circuit. But if you do not move the magnet, you are not changing the magnetic flux, then the galvanometer is showing no deflection. Same thing can be said for this also. It is experiment 2, by the way. In this case there is no physical magnet, but from Weierstedt's experiment we have established that a current carrying coil, it generates a magnetic field of its own, which deflected that magnetic needle. So since current is flowing through this coil, there is a magnetic field associated with this coil. So when you take this coil towards C1 or away from the C1, then also you are changing the magnetic flux associated, and as a result of that you are getting induced current in C1. So that's what these two experiments are about. Now there is a third experiment also. So in the third experiment, what we do, we take again two coils. In one, galvanometer is connected and the other coil is remaining fixed. There is a battery connected, there is a key also, like this. Now in this case, we are not moving either of the coil. If I call it C1 and if I call it C2, we are not moving either of them. They are remaining fixed. Now you will notice that when you turn this key on, when you close this key, even after not moving C2, the galvanometer shows a little deflection. And after closing the key, so current is flowing, when you open the key or turn the circuit off, then also the galvanometer shows deflection. That is, again, it is pretty strange. How can the galvanometer shows deflection? Because just by looking at it, there is, since we are not moving C2, so magnetic flux is not changing, then how come we are getting induced current here? Well, the answer lies in the fact that when you turn the key on, then the current does not just suddenly rise to 10 ampere, it gradually increases, like from 0, 1, 2, 3, 5, 4, like that up to, let's say the maximum current is 10 ampere. So the current is increasing to 10 ampere when you turn the circuit on. That means if current is increasing, so the magnetic field associated with it is also increasing. So magnetic field increasing means change in magnetic flux associated with C1, and change in magnetic flux induces electric current. That's why you get a little deflection when you turn the key on or when you close the key. Now after closing the key, after a few times, the galvanometer would show no deflection because the current in the circuit is steady current. Then again, when you open the key, when you turn the circuit off, what happens? The current now decreases from its maximum value, let's say 10 ampere to 0 ampere. In this case, the current is decreasing. As a result of that, the magnetic field associated is also decreasing. That means magnetic flux increase or decrease does not matter, it is changing which matters. So this change in magnetic flux will also induce electric current in C1. So that's what Faraday's experiments are about. And from these experiments, we have established the phenomenon of electromagnetic induction. So I will just quickly write down the definition of electromagnetic induction. Its short form we call it EMI, not easy monthly installments, by the way. So EMI or electromagnetic induction basically says that whenever you change the magnetic flux associated with any coil, then electric current and if there is electric current, of course there will be voltage. We call it EMF is induced in the coil. So that's what the definition of electromagnetic induction is. We are basically getting electricity out of magnetism. But the key point here is you have to change the magnetic flux. That means steady magnetic field won't give you any induced current. Only when you change the magnetic flux or change the magnetic field, then only you will get electric current in the circuit. So this is the definition. Now we will try to see these experiments visually. So let's see how they actually work. How they actually work, let's try to figure out. All right. So first we will see the weird states experiment. See, this is a coil which is connected to a battery, and this is a magnetic needle. If I make the voltage 0, then you see this magnetic needle is pointing towards north and south. But the moment you increase the voltage, what happens? If I place this coil near the magnet, you see the deflection. Can you see the deflection? I hope you are able to see. See this deflection. So whenever this whenever this current carrying coil is placed near the magnetic needle, it is showing deflection. Now if you think that is strange, because a magnetic needle cannot be moved until and unless it is subjected to some external magnetic field. So what it means here is this current carrying coil is basically generating some sort of magnetic field which is compelling this magnetic needle to deflect. And from this experiment we got the relationship between electricity and magnetism, that current carrying current or moving charges produces magnetic field. This is, by the way, Weierstedt's experiment which we discussed earlier. Now we move on to Faraday's experiment. So in Faraday's experiment, you see in the diagram I drew there, we used one galvanometer, but here there is no galvanometer. For better visual representation we have a bulb. So if current is flowing through this coil, this bulb will glow, and we will that's how we will know that there is current. So I take this magnet, I take it closer. Can you see the bulb glowing? Yes, it is glowing. It is glowing, you see? It is glowing. So this is basically Faraday's experiment. So if I change the position of the magnet, the bulb is glowing, meaning there is induced current. There is induced current when? When I change the magnetic flux associated with the coil. If I don't change it, there is no glow in the bulb. So that's why I say the change in magnetic flux is very, very crucial. Now the other one, when this time you see the magnet is being changed by this another coil which is where a battery is connected, that means current is flowing. So from Weierstedt's experiment it is established that this current carrying coil will behave like a magnet because it is producing magnetic field. So you will notice when I take this coil towards or away, then also the bulb is glowing. When I take this coil towards or away, the bulb is glowing. And that was Faraday's experiment which established electromagnetic induction. I hope you got a better understanding of the topic by this simulation. Next up, we again move back to our theory. So now, since we have established electromagnetic induction, we understood the core concept of it. Now let's move on to the next topic, which is Faraday's laws. Why laws? Because there are two laws. First one says, the first law of Faraday says, it is basically the definition of electromagnetic induction. It says that whenever the magnetic flux associated with a coil is changed, then electric current is induced. Then electric current is induced in the coil. Then electric current is induced in the coil. What's the matter of writing it again? Because of the next part. So the induced current remains as long as the change in magnetic flux continues. That's the first law of Faraday, which says that whenever the magnetic flux associated with the coil is changed, then electric current is induced in the coil, and the induced current remains or lasts as long as the change in magnetic flux continues. If you do not change the magnetic flux, you will not get any induced current. Like you saw in the simulation now, when the magnet is not moved, the bulb didn't glow. Yes? So that's the first law of Faraday. What is the second law? The second law says that the induced EMF generated in a coil is directly proportional or equal to the rate of change of magnetic flux. So we may write for the second law, induced EMF E equal to minus N d phi B by dt. This is the most important formula which we will be needing to further understand the topics in this particular chapter. Why the negative sign? I will explain in a bit. Now N is a new thing. N basically means the number of turns. N basically means the number of turns. So in this formula, the induced EMF is negative N d phi B by dt. So induced EMF not only depends on the rate of change of magnetic flux, but also depends on the number of turns of the coil. If you increase the number of turns, the EMF will also increase. Now in this statement, there is this word called the rate of change of magnetic flux. Whenever rate is involved, you will know for sure that the quantity is divided by time. So we read it as the differentiation of phi B or magnetic flux with respect to time. So this is basically the formula for induced EMF. Now about the negative sign. So I hope you understood what Faraday's laws are all about. The first law is basically the statement of electromagnetic induction with this added line. And the second law basically gives you this formula, E equals to negative N d phi B by dt. Now to understand this negative sign, why this negative sign appears, you have to know about another law, and that law is Lenz's law. Lenz's law. So we will now learn about Lenz's law. If you wish to, you can pause the video and write this down. Next we will learn Lenz's law. Lenz's law. What is Lenz's law? First I will write this definition and then I will explain. So Lenz's law basically tells you that the direction of induced current, or for that matter EMF, is such that it opposes the change in magnetic flux responsible for its production. Now that's pretty strange, isn't it? So Lenz's law basically says that what is producing the induced EMF? What is producing the induced EMF? Of course, the change in magnetic flux, and the direction of induced EMF or current will be such that it will oppose or it will resist the change in the magnetic flux which basically produced it. मतलब जो इसको बनाया वो उसी को रोकेगा, right? How? We will better understand with the help of a diagram. So which to choose? This one. Okay. So now imagine that there is a coil connected. There is a coil and there is